I'm Aubrey here, and welcome to the discussion on Module 2. Our topic is on Earth and Earth systems. In this module, we will be discussing the specifics of the Earth's formation and what subsystems make up our planet. So for our learning objectives, we have two. First, describe the characteristics of Earth that are necessary to sustain life, and explain that the Earth consists of four subsystems across which boundaries matter and energy flow. During the last part of our Module 1, we have discussed that the solar system is formed by, as explained by the nebula theory. So we have a nebula which forms a star in the middle. The materials in the middle coalesce and become a star, and then you have on the side the accretion disk, which eventually forms the planets. Okay, so let's continue that story. So for forming the Earth, our young Earth, the protoplanets, were a collection of particles that are pretty much spinning as an accretion disk. But later, it started to grow larger as these particles spin, so they start to aggregate. Now, imagine masses of rock and metal spinning around in space. And what happens is these things collide, and when collisions like that, of large collisions like that occur, you have heat and pressure as a result. So the heat and pressure due to the impact triggered a remelting of the whole planet. Okay, so what does that mean? Instead of being just normal dust particles or rock particles that are spinning around in space, they started to remelt because of the heat and pressure of the impact. And what you have instead of an aggregate of rock is this molten, semi-molten material that is moving around in space. This phenomenon is called planetary differentiation or chemical differentiation. So the melting process produced by the semi-molten body creates a differentiation process. So differentiation of elements. So imagine you have a molten ball of materials. What happens is the heavier materials, the heavier elements, particularly iron and nickel, starts to sink to the core because the gravity, the center of gravity is the core or the middle. So the denser materials like iron, they sink to the core, and then the less dense materials like silicon and oxygen are left on the surface. Okay, so the result here is that there is a differentiation process. So the heavier materials, the metal elements, make up the core. The less dense materials became the mantle and the crust. So this is a graph which is showing the differentiation process. So again, the metallic elements are what now composes the inner core and outer core, and then the lighter materials make up your mantle and the crust. Okay, so this is important because if the planetary differentiation did not occur, we wouldn't have layers, which is beneficial for us, life on Earth. So the layers on Earth wouldn't have occurred, even including an atmosphere, because the atmosphere is composed of light gas elements. So if there is no differentiation process, the gaseous elements wouldn't have separated from that rocky material and created a good atmosphere, as well as the rocky materials or the heavy materials wouldn't make our core. So without differentiation, it would just be a rocky mass, like a random asteroid floating around in space. So, but since we had a remelting process, we have layers in our planet. Okay, so to help you further visualize what does that look like, let's play this short clip. Let's mute that. Okay, so again, our planet began as an accretion disk, which floating around in space started to collide against one another. Okay, so even while those things collide, it started to gain gravity and also mass. But still, continuous collisions will result to heat and pressure, thus triggering a remelting. Okay, so you have a molten ball of material which is as hot as the sun, basically. But the good thing about our story is the here shown in this part of the clip is that the outer core, or the outer crust started to cool down, but the middle of our planet is still molten, and that's still true as of today. So our crust is, of course, it's cooled down, but the volcanic eruptions and so forth is only an evidence that our core is still blazing hot in some parts of the mantle. So core and mantle are still hot. Okay. So that's it actually for this part of the slide. Let's go next. Okay. Okay, so to give you a clearer image, so you have again a mass of rocks and other materials just bumping around in space, and then it became this molten rock of material. But there is a hypothesis in the scientific community that another event had greatly affected the formation of our Earth. So this is called the giant impact hypothesis. So according to the giant impact hypothesis, there used to be a large planet or protoplanet with the same size as Mars, and it collided with Earth during its early history. It's called Theia. So that hypothetical protoplanet collided with ours, and it shattered, of course. So some parts of the Earth and Theia shattered due to the impact, and that left debris that is circulating our orbit. Eventually, like the planets in the accretion disk, the debris that resulted from the impact became our moon. So Earth, there was an impact. This disk of debris eventually coalesced into our moon. Okay, so as you can notice, it's still an hypothesis, and it's stating that it is an evolving legacy of Apollo, because Apollo is a mission on the moon, and they are starting to compare materials from that of the moon and the Earth. That's why they came up with this hypothesis, and that is what being demonstrated in this artistic image, that there used to be a protoplanet as big as Mars collided with us, then which completed the Earth that we know today. Okay, so Earth has been formed about 4.6 billion years ago by collisions in the giant disc-shaped cloud of material. So the collisions within the accretion disk. And then we had a period called the late heavy bombardment. So this is a part of our history wherein we don't have an atmosphere, a developed atmosphere as we have before. And as you can imagine, since it's a young solar system, there's still a lot of rocky materials that have not been combined with Earth as of yet in our orbit, or we haven't completely cleared our orbit yet. So what happens is there was a lot of asteroids and comets that peppered the Earth, which eventually became part of our planet. Okay, so fast forward to 2,400 million annum, that's MA. There was now evidence of bacterial life, and that cyanobacteria is very important because they produced oxygen to the atmosphere. They were a very successful life form, and they just kept producing oxygen into our atmosphere, which changed life itself. So instead of being like carbon dioxide based life forms, we are very now dependent on oxygen. So the first free oxygen was released through photosynthesis by cyanobacteria, because the free oxygen used to be like in rocks, just inculcated is what is on my mind, but like fixed into rocks. So the oxygen that was present in our planet was fixed on rocks, but that's not enough to make up an atmosphere. So because of photosynthesis, they kept releasing oxygen into the air and created a oxygen rich environment. And that would be the formation of the Earth. Okay, so let's see. We already finished a lot of discussions about the formation of the Earth. Let's see. Let's test if you are able to get our discussions. So I will be flashing certain statements on the screen, and there will be 2 choices per statement. Let's see if you will be able to realize or figure out the correct answer. Okay, so for example, I will give the first item as an example. If Earth is farther from the sun, the planet would be warmer or cooler. So see, it's like a situational sort of question. So if Earth is farther from the sun, what can we predict? Naturally, since the sun is the source of our warmth, it would be cooler because we're farther from the sun. So the answer for this is cooler. So let's encircle that with a yellow pen so it's fun. Okay, cooler. Okay, number 2, it's your turn. If Earth were a little closer to the sun, the oceans would be smaller or larger. Okay, so if the Earth would be closer to the sun, we could predict that there would be more heat, and because of that, there would be more evaporation of water. So our oceans would be smaller. Okay, number 3, if Earth did not have a biosphere, so biosphere means all life on Earth. So if Earth did not have a biosphere, the composition of the Earth's atmosphere would be blank, the same or different. Okay, so as we have mentioned like a few moments ago, that the Earth's atmosphere would be definitely different because it was the biosphere that is responsible for producing a lot of oxygen, making an oxygen-rich atmosphere. So if that did not happen, then life as we know it would be so different. Okay, number 4, if Earth's biosphere has not evolved yet, we would have a blank oxygen in the atmosphere. So it's pretty much the same as number 3. So if our biosphere did not evolve yet, we would have less. The correct answer here is less. Since there was no life yet, there was no bacteria that started to produce oxygen, then there would be less oxygen in the atmosphere. Okay, number 5, if Earth did not have an atmosphere, its surface would have blank, fewer or more craters formed by meteor impacts. Okay, I have mentioned earlier that the heavy bombardment was caused by a lot of materials still not being cleared in our orbit, but there should be a layer that is protecting the Earth now, and that's our atmosphere. So if our Earth did not have a proper atmosphere, we would have more craters. Okay, number 6, if Earth were larger, the gravity would be weaker or stronger. Okay, so this is a sort of a physics question. The gravity of an object is proportional to its mass, meaning the bigger the object is, or the more mass the object would have, the more gravity it would have. So that's why they're in a movie, I think I forgot what it's called, John Carter of Mars. John Carter of Mars, what happened there is like he could jump high because there was less gravity on Mars. That's because Mars is smaller than Earth. And if we go to moon, they would say we would go to the moon. People would say, there's no gravity on moon. Actually, there's gravity on the moon. Rather, there's gravity on the moon. But since the moon is so much smaller than the Earth, then there is less gravity. That would be the correct term. Okay, so the answer for this is if we were larger, we would have stronger gravity since we would have a larger mass. Okay, 5. If Earth were smaller, its atmosphere would be. Okay, so this is related to the differentiation process that we have mentioned earlier, and also the amount of gravity our planet could produce. So if we were smaller, we would have a thinner atmosphere. So because there would have been less elements that would have differentiated as our oxygen, and we would have attracted less materials if we were smaller. Okay. If Earth were smaller, it would have a blank interior, so hotter or colder. Okay, so this is quite a tricky question. I want you to think about it like this. So you have baked two things. You baked a cookie and a cake. A cookie and a cake. So imagine if you brought them out from the oven, which one would cool faster? The small cookie or the large cake? So in this case, since the cookie is much smaller, it means the heat would dissipate to the environment faster. While the cake, since it's larger and thicker and more heat is within the cake, it would cool down slower. And the same goes with the planets. If our planet were smaller, it would have a colder interior because our planet is still continuously producing heat every day, and if we would if we would be smaller, it would release more heat faster. Like comparing a teacup versus a mug. So teacups cool down faster because they're smaller, but mugs, since they're bigger, they maintain more heat. Okay, so I hope you got that analogies. Okay, 9. If Earth did not have an atmosphere, life of the land surface would be less or more today. Okay, so this is quite easy, of course. If we wouldn't have an atmosphere, we would have far less life on Earth. Okay, so that should end the first part of our module 1. If you have any questions, you know how to reach me through discussion boards, course messages, email, or our group chat. Okay, that's all. Stay safe.